I'm Mannino, and I'm talking about the gas turbine experiment. I'm just going through objectives, experiment calculations, results, and then conclude. This experiment is meant to just understand the principles of a gas turbine and record temperatures, pressures, and thrusts. Calculations. This is the open Brayton cycle, which shows what the gas turbine, how it works. It has a pressure combustion chamber turbine connected to the compressor on the same shaft, and also a nozzle. This is a picture of the experiment we actually did. They have thermocouples and pressure sensors at different points in the turbine to show how things, how it changes. The first one is before the inlet of the compressor, then take another one downstream of the compressor, then fuel's injected and combusted, take another reading after that combustion happens, then after it expands through the turbine, and lastly after the nozzle. And this shows the temperature and entropy diagram of this cycle, where the compressor and turbine are both isentropic, and the dotted one right there is once again the actual case, whereas the straight line down is isentropic ideal case. So calculations done. I use first law to calculate the mass flow rate in that first equation, where the exit velocity is the same as the velocity at 0.5, so get that from this top right equation. And we also had to calculate the fraction of energy in the combustor and the nozzle, which is the heat of the combustor and nozzle effectively over the total Q of the fuel, which we calculate the nozzle and combustor Qs with these two equations where we use the temperatures before and after both of them. We also had to find the rate of compressor work. That one's pretty straightforward up top. Now, for the rate of turbine work, they have this Q term added on the end that's assuming that there's still fuel combusting or fuel burning in the turbine, since not all of it combusts in the combustor. So that Q is taking into account the fraction of the turbine, which they assume as the basically what's not burned up in the combustor and the nozzle. Also, we calculated isentropic efficiency, where you get the isentropic temperature at 0.2 with that top equation, then plug it into this bottom equation to get that. This is what I got for that. All these calculations were done with factory data and experimental data that other people did. And once I did that, the factory data was more efficient, which probably sounds about right. Yeah, so all the data that was given, kind of averaged them into the different regions. I took an average so that I could get RPMs close to the factory, since the factory only had 4 different readings. And all those calculations before kind of ran them and came out the experiment. The experimental data was higher than the factory for the most part. These are going in different directions, mainly because the fraction of one going up, the other fraction is going to go down, so that makes sense. So kind of the same thing with the work. The turbine is doing work on the compressor, so that's why it's negative. In conclusion, the sources of error possible, the heat addition is not ideal. They take into account fuel combusting in the turbine area, but all the calculations assume all the fuel's combusted before it leaves the nozzle, which probably isn't even correct either. The manual said that the turbine is at LSU is terrible, so it just said the data's not good. That's the main reason they give you the factory data too. Also, heat loss to the wall, so it's not actually adiabatic. In general, gas turbines are useful because they're mechanically simple. The actual turbines, they have things like cooling for the blade tips and stuff like that, but this one, there's just one shaft, one moving part, unlike a reciprocating engine. You get a high power to weight ratio. On the flip side, the blades have to be very precise and uses materials that are hard to manufacture, rare material, rare metals and stuff. So that's about it. Okay. Any questions?
Why do you think there's such a difference between the factory and the experimental?
Apart from that one just being broken, I'm not too sure, but I did notice the inlet temperature. So like, I guess the room temperature for this one was at 25 degrees, but in the factory it was actually like at 30 something. So, I mean, that could be one thing.
A couple of comments. The first thing in your, I think you have an appendix here, you have a lot of outliers.
Yeah.
Right? So
I trashed that. That's like, that's 4 readings, that's 1 groups. So, like, that was just destroying all the
yeah,
data.
so, right, so when you show something.
This was just the printed out for us.
Okay.
I just threw it in there.
Yeah, so you remove that thing and fit a line through this.
Yeah.
Doesn't look too bad here, but you need to remove all that.
Yeah.
And the other thing is that when you talk about your conclusion, you should show the numerical data. So your sources of error and the other things, they are not really part of your conclusion. It is the additional stuff that you talk about.
So to stop after the results?
Yeah, I mean, no, do not stop after the results. Show the key points from your results in your conclusion.
Okay,
Like
well, I threw it in the appendix slide too.
The one before?
No. Let's go back. Down.
No.
Yeah. No, like towards the end of the.
Towards the end?
Yeah.
After this?
Yeah. After that one. I just
Yeah.
threw that element there so you can see it.
Right. Here you have a lot of data.
Yeah.
But try to conclude from the data that you have in the results, like the numbers that you have, and then you conclude something.
Okay.
Like it doesn't have to be the sources of error or anything else, but it's just a conclusion from your results. Okay. Does that make sense?
Yeah. In all honesty, this is my last lab. I'm not going to do that in the future. So. But I get it. Yeah.
All right. Any other questions?